But if at any moment you want to know about your grade, you can see me. It's not like I'm ever wanting to hide something from you. And if I have your labs done and it's a lab you're asking about, I'll tell you. I need a couple more days to grade it. But on regular assignments and stuff, you can always check in to see how your grade is doing. That's fine. Okay. So let's start today's lesson on acceleration. Now, this is really an important lesson. Probably the most important lesson of the entire year. The entire year. Which is crazy to actually make a statement like that in class. And I'm not going to make that statement again. There are other lessons that are going to be real important. This is probably the most important of the entire year. And your physics career going forward. And I know it sounds really like, oh my gosh, it's like a lot of weight right to the rest of your shoulders. But rest assured, we're going to spend a lot of time on this lesson, and you will do fine with this. But the idea behind this extends to all types of physics going forward. Whether it's electricity and magnetism and it's an electron going to a particle accelerator. Whether it's an object like a truck moving down the road. Whether it's energy problems with a skier going up and down the hills. The concepts of motion and acceleration play a role in pretty much every topic we're going to look at this year. Okay, when we get to forces, we'll see how forces, F equals ma, is related to acceleration. So without acceleration, the world wouldn't be an interesting place. Think about it for a minute. If there weren't acceleration, you couldn't even move. My current velocity is what? And now I suddenly have velocity, right? So I must have accelerated. And we're going to talk about acceleration and its definition. We can go to the next slide to see that. And its definition is the rate at which your velocity changes. The rate at which your velocity changes. Delta V over delta T. Delta V over delta T. V minus V0 over T minus T0. But again, if acceleration weren't a real thing, if we could only move at constant velocity, we wouldn't exist. Because we couldn't physically move then. Think about that, right? You can't move unless you can accelerate. To accelerate, you need forces. You need friction in the floor to push off, to accelerate. Imagine playing sports and you weren't allowed to accelerate. I mean, obviously it wouldn't make sense because you couldn't move again, but like just small things. Like I was watching the Yankee game last night, and anyone that's a Yankee fan knows Didi Gregorius at short made this stab in the ninth inning. It was an incredible catch. I mean, the ball was ripped up the middle, and he out of nowhere just sprung to the left and dove fully out and caught it. That's acceleration at its finest, right? That's the concept of you're not moving, you're not moving, you're not moving, and then suddenly you have this quick twitch muscle that pushes in that direction to accelerate. So acceleration is key to any motion in real life. Again, constant velocity, sure, it makes the problem easier because everything is constant. It's easy to look at. Acceleration just makes things a little bit trickier. Now, let's look at the units for a moment. You notice I put 2 units there. The first unit I write is the exact unit from the formula. Well, the numerator is meters per second. The denominator is measured in seconds. So this is meters per second per second. Jot that down real quick. I know it sounds weird, but that's what acceleration really means. It's meters per second per second. And the way I think about that, the way I think about that is this. Meters per second per second. This is my change in velocity, again, over time. Meters per second is velocity. Per second means as a function of time. So what is acceleration really? Acceleration is how much your velocity changes every single second. So let's take a look at an image of this so you guys can see it a little bit better on the next slide. Okay, let's quick image of this. So we've got a car traveling at time 1, and the velocity is 15 meters per second. But then at time 2, which is 5 seconds later, its velocity is only 5 meters per second. Now bless you. So how much velocity did it lose? From 15 to 5, how much velocity? Over a time period of 5 seconds. So every second, how much velocity did it lose? Lost 2 meters per second every second. It lost 2 meters per second every second. Look, it lost, negative opposing, 2 meters per second every second. So acceleration is physically telling you, all right, my velocity is 15, my velocity is 13, 11, 9, 7, 5, and there I'm at 5 seconds later. So every second along the way, this object lost 2 meters per second. That's what this physically means right here. Notice that acceleration can be negative, so it is what kind of quantity? What quantity do we call that? A vector quantity. I know the word isn't there. A vector quantity. A vector quantity. So acceleration, direction matters. direction matters. And we're going to delve into that a little bit after we take a quick look at an example. Okay, we'll get a look into how acceleration direction matters. So let's start with this simple example. Again, for all these problems, the problem-solving technique is list the givens, list what you're looking for, write the equation you're going to use. Now, luckily enough, as of right now, you have only two equations. You've got the velocity equation from last chapter, and now you've got the acceleration equation from the last slide. Because this problem asks about acceleration, you're most likely going to use the acceleration equation. So, not much to really choose from here, because there's really only one equation to choose from the previous slide. In a couple examples or so, we're going to get through where we have a couple other equations to choose from. But for this problem, work through it on your own real quick. List your givens, list what you're looking for, use the previous equation, and go through the process here. Okay, so again, list your givens, list what you're looking for, write down the equation from the previous slide, and practice going through the solution. Use your units to help you so you know what's happening in this problem. I'll do it also, but I'll delay my work. So if you want to look up every couple minutes to check your work, or every 20 seconds to look at your work. Feel free to color code stuff in your notes, right? That might help you this year. I think it's a really good technique. I notice a lot of students do it, and now with notability stuff, or highlighters, you can bring colored pencils. You can really help yourself by color coding certain things. So I've listed the givens on the page, and then I recognize that it said how long will it take. It doesn't directly say find the time, but when it says how long will it take, how long is time, versus how far will it go. That's displacement. Maybe jot that down if that helps on the side too for problem solving. How long will it take versus how far will it go are two very different questions. How long will it take is time. How far will it go is displacement. So again, I've got two formulas to choose from. I could go to last chapter and look at this one, which was delta x over delta t. Or I can use this chapters and use delta v over delta t. Now, because I'm clearly working in this chapter, or this section rather, we're going to most likely use the bottom one. But it also makes sense not to use the top one. Why can't I use the top equation? Why do I have to say, oh, hell no, I'm not using that equation. Why do I have to say that? Yes, correct. Nothing about position. So right away you can't use it. What else? Yeah, the first equation is only valid for constant velocity. Maybe you jot that down somewhere. That this equation can only use for constant velocity. So the minute you have acceleration, you rule this equation out. Throw it out the window. It's done. There's no chance of using it. And the minute you have acceleration, you can't use that equation. The three equations from this section are all going to involve acceleration because we're looking at the topic of acceleration. Okay, so the old formula is worthless right now. So we know we're looking for t. I wrote down delta t in the formula. Well, if we start this problem in the beginning, what can we call t0? 0. Whenever you start a problem that doesn't give you an initial time and a final time, call t0 just 0. Say it started at 0 seconds, which makes sense logically. Ready, set, go. You start the race, no time has elapsed until you start, right? So for these problems, when you are subbing in, we're going to have v minus v0 over t minus t0. You can absolutely drop off the t0 for a lot of them. Because a lot of the problems will just give you a duration of time. So you assume you started at 0. Okay, if it says 10 seconds have elapsed, make this 10 minus 0. Now, we don't know how much time has elapsed. We're trying to figure that out. So we need to solve for t. Algebraically, what's the quickest way to get t by itself here in this equation? Yeah. A and t can switch spots. And again, The math behind that needs to be known in this course. All I'm doing is multiplying by t and dividing by a at the same time. It doesn't make sense in a physics course to show every single step of algebra along the way. Because for the most part, you've recognized that these kinds of tests, subject test, AP test, they're very time sensitive. Because physics is the kind of test where if you don't know it, you've got to think through it, right? You've got to think through the process, which takes time. So save time anywhere you can. So anytime you have an equation that's triangular like this, or even a proportion, you can always switch diagonally. You can always switch diagonally. And that comes from math in like 7th grade. You learned that actually. It was called the product of the means equals the product of the extremes. Probably not even ring a bell to anybody. That is what you did then. So switching diagonally is okay because you're just really dividing and multiplying at the same time. And then we just plug in. V initially was, V final is 0 because this object comes to a complete stop. Right? A complete stop means that the velocity at the end, v, is going to be 0. It's going to be 0. Now recognize, my acceleration was negative. I'm going to get 0 minus 9 meters per second all over negative 1.8 meters per second squared. And that makes sense. Negative divided by negative yields a positive. Write it down if you didn't write it down last class. Time cannot be negative. You're never going to get an answer where time is negative that's reasonable. What do you do if you do? It'll be a quadratic. You get 2 solutions. And you reject the negative solution for time. And you can absolutely get negative displacement, because we've talked about displacement being a vector quantity. You can get negative acceleration, but time is not going to be negative. If you get one answer, and the answer is negative, you probably made a mistake. But if you're solving a quadratic where one is positive and one is negative as an answer, you're just going to reject the negative answer and keep the positive answer.
I've seen like a couple problems they put like D1 is like -2 and 2 is like 4.
On a problem set in the textbook, I doubt it. I don't think they're ever going to write a negative time. But if you did see that moral, it's just the duration that matters, right? Delta t. So hypothetically, if you went from -2 seconds to 4 seconds, duration is just 6 seconds. So you replace delta t with 6. But the textbook you guys are using should not have a negative. At least I haven't seen a problem like that. Maybe like online as you're searching through problems, you might see authors writing that. But you're traditionally not going to see something that starts with a negative time. Okay? Now, theoretically, could it? Sure. Like, Maura, you could be at the starting line, right? And I could be next to you, and I could start 2 seconds early and get a head start. And you could say that I started at -2 seconds, you started at 0. Or I could say I started at 0, you started at 2 seconds later. Do you see the same how they're 6 and 1/2 dozen? So a negative over negative yields a positive. The value we're going to get for this is 5 or around 5, right? 5. 18 over 90. Yeah, 18 into 90 is 5. And what are my units for time here? Seconds. And if I don't know that, let's take a look at the unit analysis to show this. So let's do a quick unit analysis at the top. We've got meters per second divided by meters per second squared. That's what's happening right here, right? Everybody see it? Meters per second over meters per second squared. So what happens? I can show it mathematically so you can see it. But going forward, I'm just going to talk about this. Watch, ready? Instead of dividing by a fraction, we multiply by the reciprocal. Good, reciprocal or inverse, either word. So I can rewrite meters per second over meters per second squared as meters per second over second squared per meter and multiply them instead now. And what happens to meters? And what happens to one of my seconds? Yeah, they reduce, they cancel. Cancel, cancel, cancel with one of these, and I'm left with units of seconds. Now, it's really important that you pick up on the next thing I'm going to say, because it's going to save you a little bit of time in the long run. I don't want to have to do this every single time I have units, right? It doesn't make sense logically. So first, I know that if time is here, it's going to be seconds. So at least I know that. But let me show you something that most students seem to miss in math some point along the way. Look up here where I'm going to point real quick. Look at this equation right up here, right? Or this unit analysis. Meters cancel with meters. This seconds cancels with this seconds. And it becomes a unit of 1 over seconds. Does everybody see what results in black there? The top becomes 1. The denominator becomes 1 over second. And what's 1 over really? When you do 1 over in math class.
You multiply by seconds over.
Yeah, so it just becomes what in the end? It just becomes seconds. So whenever you have something that's in the denominator of the denominator, and that sounds weird, but it's what I'm saying, the denominator of the denominator really bumps up to the numerator. If that's not up here, write it down. Okay, a unit or a variable that's in the denominator of the denominator can bump up to the numerator. Because really you're just dividing by a reciprocal, which is multiplying by the inverse. You're dividing by a reciprocal, you're dividing by 1 over something, and then you multiply by the reciprocal itself. All right, let's continue. So the second part here is to talk about this concept of instantaneous again. Instantaneous. So it's the same thing as instantaneous velocity was. If you remember, instantaneous velocity was the velocity at an instant, not over a long time period. So again, we look at the same equation for acceleration, which is delta v over delta t. But if I'm looking at an instant in time, what does delta t become really? And we can see it in this problem. It becomes 0, because it's reducing. So if I wanted to know what my acceleration was from the beginning to the end, I might have a duration or a time period. But if I ask you, what's the acceleration at 2 seconds? Well, there's no way to use a formula for that. I mean, in calculus, you're worried about that, actually, I shouldn't say that. Right now, there's no way to use a formula for that. So we use this concept of what we called a limit last time. We look at the limit as we look at a time period that's getting smaller and smaller. Well, that idea, that concept that we're going to look at really, is really an easy way to see it graphically. So if we look at the next slide, we can take a look exactly here to see what we're talking about. So if we look at this graph, we can see that the velocity changes. How might you use your words and describe the motion of this particle based on this graph? And again, this is not position. Keep in mind, this is not position right here. So what might you say?
It gets faster.
It? What is it? Physics?
Particle.
The particle gets...
Sorry, the velocity
Good.
increases, and then between point A and point B, it keeps increasing, but at a more steady rate, and then it stays the same
At
B.
Okay, and then?
And then the velocity decreases when we go down to C.
Good. Now, I want someone to tell another story, but not using the word velocity and using the word acceleration.
The acceleration increases from the origin to end.
Velocity increases.
Or the velocity increases from the origin to
So what is the acceleration?
zero. Constant.
I know, this is a tough one. It's not constant necessarily here. The velocity one is easier one to say. Acceleration not as easy. Hold on, more a minute.
The acceleration is positive going up to A, and then it is less positive and then it becomes 0.
And then because it's a constant velocity up here, the acceleration is 0 at B.
And then it becomes negative acceleration as it goes down to C.
So what are we looking at here? Why was I using the pen? What are we looking at again? The what of the graph? Isabella? The slope, that's the word. The slope of the graph, the slope of the graph. So what we're going to notice again is that the slope of the velocity graph is really just acceleration. Huh? You hear Mr. Donishek? Can anyone hear that? And there's 0 acceleration. He literally was just talking about acceleration too. So yeah, we recognize that it's the slope that matters, the slope that matters. And think about that logically, it makes sense. Think about it. Go to point B, that's where it makes the most sense. At point B, isn't the velocity a constant? And when velocity is constant, what is your acceleration? 0. And what's the slope up here? So it just makes sense, especially in flat regions. Okay, now in the increasing region, it also makes sense, but you have to say the words. The velocity is increasing. Oh, what does increasing velocity mean? It means that positive acceleration. That's because the slope is positive. But then, as Mauro mentioned, look at the slope. It becomes less positive, less positive, less positive, 0. And then the slope becomes negative. And when it's negative slope, it means you have negative acceleration, and therefore your velocity is decreasing. So the concept here is very, very much like velocity with the position time graph. Remember, for position time, the slope was velocity. For velocity time, the slope is now acceleration. It's not that this is like a coincidence. There's a reason for this. We'll learn more about this year, but more really in calculus and in physics next year about the connection between these equations.
So that means from B to C, it's the acceleration is
increasing because the slope's negative, or what does that mean?
So you can't really say what the acceleration is doing unless you measure every single slope along the way, Jack. So right here, this acceleration is 0. Here it becomes negative. Then it becomes more negative, but then look, it becomes less negative. Then it's a pretty constant acceleration the whole way down. That hasn't changed. Then the acceleration becomes more negative. Then the acceleration becomes less negative. You follow what I'm doing? You see how I was shading?
Negative acceleration is just
A decreasing velocity in general. Now, we don't know if the acceleration is necessarily increasing or decreasing. We only know that based on the slope of the line to tell us more about the acceleration itself. But we can definitely say that, yes, in this region, acceleration is less than 0. In this region, acceleration is 0. And in this, I'll put little marks. And in this region, acceleration is greater than 0. We absolutely know those 3 facts. Okay? Until we really start to measure slopes at every moment, though, we can't really say much about the acceleration unless we visualize it. Positive acceleration, getting less positive, and then 0 on top. All right. Let's make another note here. Let's make another note. We talked about this with velocity. If the acceleration is constant the whole time, what can you say about the average and the instantaneous accelerations? They're the same. Let's write that down. If the acceleration is constant, then the instantaneous and average acceleration are the same. Again, if the acceleration is constant, then the instantaneous and the average accelerations are the same. And think about that logically. Draw yourself a graph if you need to. Like if I drew a graph of acceleration where acceleration were constant, this is what it would look like. Ready? There's my graph. That's acceleration being constant. Well, at any moment along the way, the instantaneous acceleration is just whatever the value is. Because again, this is an acceleration graph. So it's whatever this value is at any point. So we can call this 7 meters per second squared. So at any moment, the acceleration is 7 meters per second squared. And at any moment, for the entire duration, what's the average? 7 meters per second squared. So whenever you have a constant acceleration or a constant velocity, it tells you that the average and the instantaneous are going to be the same. That's a great multiple choice type question, especially for like a standardized test you might see. Yeah.
For a velocity graph that represents this, it would be a linear.
Correct. Very good.
For x would be exponential.
Nice. Very good. We're gonna get to that in a little bit. Very good, Valentina. So the velocity graph representing the motion she was just referring to at the bottom there would look like that, because constant acceleration of 7 means the slope of this graph is always going to be 7. Right? Think about that logically. When we had that on the first test, I gave you guys a velocity graph, right? And said which position function matches it. That's actually what you're doing there is calculus, believe it or not. Going from something like velocity up to position, or from acceleration up to velocity. And again, because this is a constant acceleration, it means that the slope must be constant the entire time. So I can tell you that that equation is definitely going to be 7 times t, and that's going to equal v. And I know that because, look, down here, the value of acceleration I listed was 7. So it means the slope of that function has to also be 7. Okay? Again, the slope of the velocity graph is the acceleration. Yeah?
So that means after 7 seconds, the object, whatever it is going 49 meters per second?
After 7 seconds have elapsed, it would be at 49, assuming it started at rest, yes, it would be at 49 meters per second. Because every second, it's gaining 7 meters per second.
Is there a limit to that? Or?
Well, technically speaking, yes. The speed of light is the limit.
Yeah.
And there's also a physical limit if an object is dropping due to air resistance called terminal velocity.
Right.
So we'll talk more about that. But theoretically, no, there's not. It will just continue to go up. But realistically, absolutely, there is a limit. Let's look at this table here. Let's take a look at this table together. And what I want to do with this table is just comment. Comment on the possible velocity initially and acceleration that would cause this type of motion. So, real quickly, tell me, what are some scenarios where you speed up? Like, how could you physically speed up? If blank and blank. I want you to fill in those blanks. You can speed up if blank and blank. Tell me about these two things. Christina.
You speed up if you are starting a race and you want to go faster at the end.
Okay, now use the words velocity and acceleration. Same question. Speed up if?
If you are starting a race at
accelerate at the end. Can somebody tag on to what she said? There's one other thing I want to say.
Accelerating positively.
Good. So it's the direction I want to talk about. So Christina's right. If you start with a velocity that's constant and you're accelerating toward the end, you're speeding up. But remember, it's a vector quantity. So when your velocity is positive initially and your acceleration is also positive, it means you must be speeding up. And that motion can be described and seen with this eraser. It's moving to the right, it's getting faster, it's getting faster, it's getting faster, because it's accelerating positively. Now, first of all, how many in the room run at some point, cross country, track, right? Okay. Or we've run for exercise at least at some point in our life. We've all run, man. So when you're running,
Never gonna go fast
I've never run in my life.
I only skipped.
So when you're running, what do you feel against you when you run? What do you physically feel? Air, right? Air resistance. So while you're running, you're always experiencing what kind of acceleration while you're running? You're always experiencing negative acceleration. Now, what if I'm running left though, Mauro? If I'm running with left velocity, then what kind of acceleration am I feeling actually? So that idea is kind of weird, right, to think about. So let's discuss this idea for a second again. If I'm running and something's slowing me down, I know that the wind is opposing my motion. Opposing. So we use the phrase deceleration in physics to mean that something is simply slowing down. So we're going to get to the second case in the first one still. But looking at the second category here, when we see slowing down, let's jot down the word decelerating. And decelerating is a word that is thrown around too liberally. It's like thrown around too much in certain circumstances, but it's not true. So, just because you have negative acceleration does not mean you're decelerating. It just means deceleration that you are at opposing values. So if I'm running this way and the wind is pushing back, that's deceleration. But if I'm running this way and the wind is pushing back, that's also deceleration. So deceleration is not about the sign of acceleration being negative or positive. It's about your motion slowing down. So the first case was negative, negative. Why does this second case I'm going to write for the first one make sense? For speeding up. How come negative, negative after positive, positive for speeding up works? Why do you still speed up, Jack? What do you think?
Two negatives makes a positive.
Okay. It's a good way to think about it. And that's a good way to remember it, by the way. That's actually a really good way to remember it. Two negatives make a positive, being positive, speeding up. That works. Okay. But physically, yes.
Speed isn't a vector quantity, so speed can only be positive. So the more negative your velocity is, the more positive your speed is. So if your acceleration is making it more negative, making your velocity more negative, then you're technically speeding up.
But in what direction, Mauro? In the negative direction. Do you hear what he's getting at there? The speed has to do with your actual motion, not the direction. So if I start with negative velocity, but then acceleration pushes me forward with more negative acceleration, making it faster and faster and faster, or my velocity more and more and more negative, I'm getting faster, just in the negative direction at that moment. So as Jack said, you could think two negatives or two positives make a positive, right? Either direction there. Now what about slowing down? As a result of what Jack said, what do you think is going to happen with slowing down here? What is your guess or what is your idea? Janice, go ahead.
It would be a positive and negative.
Good. Or?
Negative and positive.
Very good. So either of those scenarios involve deceleration. And that's what we just mentioned. If I'm moving right, but the wind is pushing me back, I'm decelerating. If I'm moving left, but the wind is pushing me right, I'm also decelerating. So deceleration simply means that your velocity and your acceleration have opposite signs. They disagree. It's like a tug of war. Okay? It'd be like me pushing a couch across the room, and then you're waiting here and just be a jerk and you like push back against me, right? It's slowing you down. You would be negative acceleration, I would be positive velocity, we would battle. And as a result, it would slow down. The motion would slow down. Okay, so that's what deceleration is. Really important that you understand that word, deceleration. Because you're going to see it on quizzes, on tests, on problems, and you need to know that if you see the word deceleration, it doesn't mean that your acceleration is negative. It just means it's opposite your velocity. So if my velocity is negative and I'm decelerating, my acceleration is actually positive. Again, they oppose each other while decelerating. How about this last couple here? How can you have constant velocity? How is that possible? How is that possible? You can think of this from last. Yeah, Juliet.
If you have could you have a positive or negative initial velocity, but then no acceleration?
Very good, Juliet. Okay, 0, and I'll write the word 0 actually, because look at a circle now. When you have 0 acceleration, it doesn't matter what your initial velocity is, it will be constant. Very good. Second one. How about after that? Speeding up from rest.
0 and then any velocity and any acceleration.
Very good. Positive or negative again there. Very good. And again, I'm not moving. And if I get positive acceleration, I go this way. If I get negative acceleration, I get pushed this way. But either way, I'm speeding up from rest. And then the last one. Yeah, very good. I saw everybody go like this. 0, 0. Yep. You have no initial velocity, and you are not moving only when you have both equal to 0. This table is really, really useful. Okay, keep that in the back of your mind. Keep this idea in the back of your mind. And the way I organized it, I did on purpose so that you have the concepts tiered together, or tied together here between the two. Okay. Continue. All right, so let's look at one more example of a theoretical one, and then we're going to get into some heavy math after this. And the heavy math we're going to get into, I know we have so much time. The heavy math we're going to get into is a derivation, it's called. And I'm only doing this in an honors course. I don't really do this in a regular physics course. A derivation is going to show you in a minute where equations come from. Okay, we're going to come up with 3 new equations as a result. So let's start with this problem first, and we'll get into that little bit of heavy math. So we look at the problem. It says, if the velocity of an object is 0, does it mean the acceleration is 0 automatically? If the velocity of an object is 0, does it mean the acceleration is 0? If the acceleration is 0, does it mean that the velocity is 0? So let's just talk this through. Based on our last table, it would help for sure, but let's talk it through. So how about the first one? If the velocity is 0, does it mean that the acceleration has to be 0? What do you think, George?
Yes, because if there's no velocity, there's no speed. Wait, no, not necessarily. But if the velocity is 0, there's no way it could be moving. So.
What do you mean?
If the velocity is 0, and let's say that if the velocity of an object is 0, that means that it can't move. So if it can't move, then the acceleration has to be 0 as well.
I get the argument.
And wait, no, unless you go back to your starting point.
Okay, so that's the case that is not true, right?
Yeah.
So George was thinking for most cases, oh, this is true, or if you have 0 velocity, you can't have acceleration. But then he came up with one case, it seemed. Can you explain that case a little more?
Well, if you go back to your starting point, that means you did have some speed, and that means you could have some acceleration, but your velocity is still going to be 0. So your acceleration could be positive.
Okay, now remember, for this problem, it's not saying average velocity over the whole period. So if you look at the wording of it, if the velocity is 0, does it mean the acceleration is 0? They're really referring, it's right out of your textbook, it's really referring to instantaneous velocity and acceleration. So is there a possibility that there's an instant where your acceleration is positive or negative or some number, yet the velocity is 0? Can we think of a scenario like that? Because I can think of a scenario, actually. I like your logic, George. Your logic made sense, but then you thought of the one possibility you talked about returning to your spot. That's a good example to think about, but I need more than that. What do you think?
No.
No? Anybody think of something? It's not easy to think of a case like this. Yeah?
I could try. If you were accelerating, but you were going if you had a negative velocity initially,
Negative velocity, let's do this, okay?
and then you're accelerating, and then
Which your acceleration, positive or negative?
positive,
Okay, so it wins against me.
and then you pass 0, so your velocity becomes 0, but you're still accelerating now.
And then what would happen after it's 0?
Eventually come back this way.
Let's talk about that for a second. That's right, very good, Laura. That's very good. It's the turning point is the problem here. The turning point. That's when you said turn around, go back to your spot. So what happens, the easy way to think about it, I'm going to explain it a little bit simpler. Think about a trampoline. You've been on a trampoline at some point, right? Or you know what a trampoline is like. Okay. You're jumping on a trampoline, right? When you jump on that trampoline and the trampoline gets stretched all the way down, what happens at the very bottom of your body for a moment? You stop for a moment, don't you? you're moving down, which is negatively, and then you stop for an instant in time. And then you start to move upward, don't you? Well, your velocity went from being negative to being positive. So your velocity changed, didn't it? And the definition of acceleration is a change in. So when you are jumping on a trampoline, the trampoline springs are accelerating you upward. So the whole way down, here's your body, hits the trampoline, the springs stretch, the springs are pushing back against you. This is called Hooke's law, we'll learn about later this year. Hooke's law causes a push back in the direction, which will cause you to get launched upward. So the entire time on the way down, when you hit the trampoline is pushing back up with acceleration that's positive. So your velocity is negative, 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 negative. You stop, and then your velocity is positive, 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 and then it launches off. And then we didn't talk about gravity yet. We're going to get to that soon. But what does gravity do? Which way does gravity pull you? Down. So the whole way up, which way is gravity accelerating you now? It's accelerating you down. And then what happens at the top? What do you do again? And then you turn around, don't you? So at the top and at the bottom, what's your velocity at both those moments? Yet you have acceleration at both those times. Because again, gravity is always pulling you down. Whether you're moving or not, it's still accelerating you. And the spring in the trampoline is always pushing you up when you're in contact with it. So it's the same problem as what Morrow said, except it's just different when it's left to right. So if I'm moving leftward, but I've got, like, say, a thruster off a car. So here's the car, all right? Here's like a rocket booster on the back of the car. So, here's actually, what I think about would be like, like reverse thrusters on like the SpaceX. Anybody follow Elon Musk and the SpaceX stuff he does with the landing rockets? So those self-landing rockets have reverse thrusters that fire in all directions to keep it stable as it lands. Your velocity is downward, yet your acceleration, your velocity is downward, and you're pushing like that into the ground, which accelerates you upward, which is what causes the rocket to coast. So this is what you're seeing visually. This is the thruster. As the object is moving, the thruster is pushing that way, so therefore it's pushing you back, and then eventually the thruster causes you to stop, and then if it kept thrusting that way, it would push you forward. So eventually you're going to stop and then turn around. The moment that you stop is when your velocity is zero, yet you do have acceleration still, that instant in time. Now how about the second one? The second one is a little bit easier, I think. The acceleration is zero doesn't mean the velocity is zero automatically. If the acceleration is zero, does it mean that your velocity is zero automatically? What can you say about this? I'm seeing the same hands. I'm not ignoring you guys, I promise. I just want to get other people interested. If your velocity or your acceleration is zero, does it mean that the velocity is necessarily zero? What do you think, Justin?
No, velocity is constant.
Good. The velocity could be constant. Yeah, it could be zero, right? Because zero is a constant. But the velocity could still be a value of 5 meters per second, feet per second, miles per hour, whatever it may be. Yet the acceleration is zero if that velocity doesn't change. So the second answer is, if the acceleration is zero, does it mean velocity is zero? No. Again, because the velocity could be constant. These are two questions that are asked on like every subject test, every AP exam, the concept behind this. Now, it might not be directly asked in these exact words, but the idea of differing acceleration and velocity comes up over and over and over again. So I'm introducing it to you here, but in your homework you'll see I asked you other questions that involve this idea again, and then I can guarantee you on your test you'll have something that involves this kind of a concept, where if they have one is zero, does the other one have to be zero automatically? All right, let's start this derivation that we're going to get into for a little bit. So this, I say heavy math, by the way, only because we're going to be doing a lot of math with all equations and not numbers. So it might seem heavy because it's going to be all variables and seem like, wow, there's so much going on. But how many people, show of hands, how many people feel confident in substitution principle or substitution method? I hope everybody, okay. It's all right, if not. What I mean by substitution is substituting one equation into another. That's all this is going to be. So if you feel like you're getting lost along the way, stop, pause yourself, and say, what am I doing? I'm simply substituting one equation into another. That's all we're going to be doing. But we're going to do it several times over and move some stuff around algebraically, so it may seem a little bit tough at first. So, to get our first equation, we're going to start, and the first one is very simple, real simple. Start with the definition of acceleration. The definition of acceleration is delta v over delta t. So this becomes simply v minus v0 over t minus t0. Now, for all of these equations that we're going to look at now, we're going to make the assumption that t0 is 0. So let's jot that down at the top. Oops. Let t0 equals 0. And simply put, let all the problems start at time equals 0, meaning at the beginning. So what this does to this equation is it makes it simplified a bit. V minus V0 over t. Now, the first equation that we're going to really care about is this one right here, but solve this for V. Just solving this for V. Multiply by t, add the V over. Again, multiply by t, add the V over. I'm going to solve this for V. So again, this is going to become AT equals V minus V0, or V equals V0 plus AT. And that's our first of the three main equations. V0 plus AT. Anybody see any sort of interesting nature about this equation if they look at it? I know it's weird, and I don't know how I can say this right. Anybody see anything about functions when they look at this equation is what I should say. Functions. What are you seeing, Christina?
It reminds me of the y equals mx plus b.
Y equals m, slope is acceleration, x plus b. What was b in all math problems? B was the starting value, y-intercept. Well look, starting velocity. Hey, what did we say acceleration? Acceleration is the slope of the velocity graph. And look, the acceleration is right in the spot where slope would be. This is m. X, which is normally your x-axis. What do we call the x-axis in this class? Time. That's t. So this is really analogous. This is analogous, maybe jot it down below, to y equals mx plus b, or b plus mx. I'm putting it in a direct order. So your v0 is your starting value, your acceleration is your slope, your time is now your independent variable, and your dependent variable along the y-axis is your current velocity. So this equation is extremely useful, and we're going to see how it behaves as a linear function, really. Behaves as a linear function. What would that look like graphically, just so we can see it? I'm going to put that below. Graphically, I would just illustrate that as follows. Okay, that's how I would illustrate that graphically. The y-axis is v, right, which is here. That's y. The x-axis is time. The slope is acceleration. We said the change in y, the change in x is acceleration. And the starting value, or the y-intercept, is your initial velocity. That's what that would look like graphically when I think about that equation. Now, whether you realize it or not, you guys already did this in the lab the other day. Remember the lab the other day? The velocity graph just looked like that the whole time when you push the push cart up? So you're going to start thinking about this. And why did the velocity have a negative slope? Because when you push the cart up, what was it accelerating? In the negative direction, or deceleration. So it was slowing down the whole way up. So as a result, this object eventually came to rest in the lab. Here, we're just seeing the positive incline. Maybe it comes back down, or maybe the velocity gets lower. But that's the general shape of that one. Now, for the second equation we want to look into, let's start off with this idea of the definition of velocity from chapter 2. And that definition, actually, I'm going to put it over here. The definition of velocity from chapter 2 was v bar equal delta x over delta t. Remember, that was the definition of velocity from chapter 2. And we were told in this part that we could say, all right, well, v bar is really x minus x0 over t minus t0. Well, again, t0 drops off because we say that t0 is simply 0. So that's the equation I have. And you might for a minute be like, this isn't helping me at all. But I know this right. You did this last chapter. You can multiply by t, add the x0 over, and you get x by itself and the position function. We can do that like we did in the last chapter. But what we're actually going to do is we're going to do a little bit more than that. So let's first solve this for x like we're saying. So we'll multiply by t on both sides. And then move the x0 over by adding it. And again, this is nothing new. We saw this equation last chapter. for those of you, remember for the Arthur-Betty problem, this was the equation you really wanted to use in the Arthur-Betty problem. Position equals initial position plus velocity times time. Now, for this equation, though, there's something unique we can do. We can actually recognize that in this problem, we are looking at, it's italicized, constant acceleration. And when acceleration is constant, I can look at this graph, take a look at this graph down here, and I can recognize that, well, what's the average velocity going to be in this problem? If it's constantly accelerating, the average velocity is right in the middle. It's smack dab in the middle, right there. Again, if it's constantly accelerating, the average velocity will be this number right here, which is really just the average of these two values. Give me one more second. So you can do this. You can rewrite this as average velocity and take this equation and substitute it right in there for V bar. We're going to pick up with this tomorrow. Listen, your homework at the end is far more extensive than what you can do tonight. But there are a lot of problems that are theoretical in the beginning. You can do those ones already if you'd like to. Okay, so I'm going to see you guys again on Thursday. We're going to finish this lesson. We're going to do a lot of math problems, and your homework has a lot of math problems. But, again, any of the homework problems that don't involve math, if you want to get a head start in the next few days, you can do so. Okay? Have a good day, guys. Good job today. It was a lot of work. I appreciate it.